So far, looking at angle measurements, we've described these measurements in degrees. But there's another way that we can describe these measurements, and that's in radians. So part of the name radians is the radius. So this measurement of angles is depending on the radius of the circle. So let's talk about how we can visualize this measurement of 1 radian. So we're going to have to use our imagination a little bit because this is a computer screen and it's difficult to show. But just imagine, say I had a piece of yarn and I measured it out so that it laid right across the radius there. So I'd have this piece of yarn, I would have it start at the center and go out to the edge of the circle, and then let's say I cut it. So I have this piece of yarn that's exactly the length of the radius. Then what I would be doing is I would pick up that piece of yarn and I would have it start right there. And let's say I go in the positive direction and I lay it down along the outside of this circle, maybe to about there. So I have the same piece of yarn, I lay it down until it ends, which we're going to say it ends right there. So what we've created here is kind of using an arc length, but without going too much into arc length, let's say I imagine this measurement right there. So along the outside here, we have this arc length that's equal to the radius because it's based on that piece of yarn that I laid down. Now, if we talk about this angle measurement that's in the middle here, that is 1 radian. So it's this angle measurement that's created based on laying down this distance of 1 length of the radius along the outside of the circle. And then you can imagine I pick up that piece of yarn and do it again, which would maybe take us to about there. And that would create an angle measurement of 2 radians. And if I did it again, 3 radians. And then we could just keep doing that around the circle. So it's a way of dividing up the circle based on the radius of the circle. So we have these measurements based on that. So now let's talk about converting these, because right now it doesn't look great in terms of converting to where are these landing in regards to degrees, which we're just getting comfortable with. So let's talk about what's happening at 180 degrees. What I can see is happening at 180 degrees is we're going 1, 2, 3 radians, and then I need a little bit more. So visually, what I would see is 3 radians plus a bit more. Well, what's a common number that we've seen a lot? That's this idea of 3 and a little bit extra, and a little bit extra that's not a pretty number, pi. And that's exactly what's happening. If you, and this is hard to do like physically with a piece of yarn, but if you lay down that piece of yarn pi times, so 3 and a little bit, it lands exactly at 180 degrees. So this 3 and a little bit more ends up being exactly equal to pi. And it would be pi radians. So using that radius of the circle. So 180 degrees as a conversion is exactly equal to pi radians. So then if we wanted to go further in terms of how many radians are in 1 revolution, so going around the entire circle, so 1 revolution, which is the same idea of 360 degrees, well, that would be the same idea as like double 180 degrees, which would mean in terms of this conversion, if 180 degrees is exactly equal to pi radians, then it would just be double pi, which means 2 pi. So 360 degrees is going to convert to 2 pi radians. So in terms of measurements along the outside of the circle, and we're going to ignore degrees for a moment here, but it's this idea that we can have these angle measurements of 1 radian, 2 radians, 3 radians, pi radians. And then we start at 0, but if we make this full revolution around, that's the same thing as 2 pi. So we're getting these different numbers coming through, and they're based on the radius of the circle. However, you can play around with this. If you just find some string and print out a circle, they land in just about the same spot. Like if I made a bigger circle, this radius and its ratio to the outside of the circle stays exactly the same. Just like how degree measurements stay the same. 30 degrees on a small circle is the same as 30 degrees on a very large circle. But it's just in order to find these spots along the outside of what's representing 1, 2, 3, and pi is coming from the radius and moving along that distance of the radius along the outside of the circle. So that's what radians are. It's how we can visualize 1, 2, 3, and it's just that 3 ends up being pretty close to 180 degrees. We just go a little bit further in order to get to exactly 180 degrees, which will be the equivalent to pi. So let's start relating this to degrees a little bit. And with that, when we talked about the angle measurements in degrees, there were those key increments, the 45, 60, and 30. And it all comes from dividing up. We talked about dividing up 360 degrees. So we're going to approach this the same exact way. It's just instead of dividing up 360 degrees, we're dividing up 2 pi. But it does just come down to these methods of dividing it up. We're just going to have some fractions to work with. So these increments of 45 degrees, thinking about that in terms of radians. So what we talked about is here's going to be 0, here's going to be pi. Now what I can think about is we're taking this distance of pi and we have divided up perfectly into fourths. So to just go 1/4, to measure that, I would just be taking pi divided by 4. So that is 1/4 of pi right there. If I go 2/4, and in fact, I'm going to write that up above here. If I go 2 of those fourths of pi, I know that's a weird way to phrase it, but it's like we've gotten 1/4, 2/4, which is the same thing as pi divided by 2. Which makes sense if we have this entire distance of pi here, that's just coming from half of pi. And then if I go 1, 2, 3/4 of pi, that would be 3 pi over 4. So I like to show this unsimplified form because it really comes down to counting around the circle. I mean, now we're throwing in fractions and things like that, but if you know those 45-degree increments are coming from a denominator of 4, and we're going to have pi coming through in the numerator because that's what we're dividing up, then what it comes down to is 1, 2, 3, and then when we get to pi over here, that's like 4 pi over 4. And I could just do this all the way around. Like this would be 5 pi over 4, 6 pi over 4, 7 pi over 4, and then getting to 8 pi over 4, which is just 2 pi. I'll write these closer. I like to write them off to the side just in case I need to reduce down. That doesn't reduce. This does. This is 3 pi over 2, and this is just 7 pi over 4. So in a simplified form, it comes down to recognize you have a denominator of 4. That's going to link to 45 degrees, so pi over 4. And then in terms of going around the circle, you're just counting 1, 2, 3, 4, 5, 6, 7, 8. And then you just reduce down. So in radians, those are the angle measurements. And then we do have this conversion of like Pi over 4 is the same as 45 degrees, 90 degrees, 180 degrees, 270 degrees. Those are there. We're just using a different angle measurement. So let's talk about in terms of increments of 60. So we have 0 radians, we have pi radians, and what we're doing with 60 degrees is we're taking that distance of pi and dividing it up into thirds. So this would be pi over 3. And just like I did with pi over 4, it's the same idea of just counting around the circle. I know I'm going to have that denominator of 3. I know I'm going to have pi in the numerator. It's just the idea of one of them, 2, 3, 4, 5, 6. So this would be 2 pi over 3. Where we're getting pi, that's the same as 3 pi over 3. We have 4 pi over 3, 5 pi over 3, and then 6 pi over 3, which is just the same thing as 2 pi. So those are our measurements for 60 degrees. That relates to pi over 3. And our last one here with increments of 30 degrees. So we have, and in fact, I can fill in the ones that we've already found. We don't need to find them twice. I'll still talk about the idea of counting around the circle. We have pi, we have pi over 2, we found that already. We have 3 pi over 2, which we found already, which that's another counting. It's like 1/2, 2 halves, 3 halves, 4 halves. We have our measurements from 60 degrees in here. So pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. So those are already found. So now let's talk about what 30 degrees does though. So we have this distance of pi, and what we've done is we've cut it up into 6 even pieces. So this one wedge here from 0 to this line would just be pi over 6. So you could think of that as half of the third, or the fact that we have 1/6 of pi. Then just to show you the counting, because that's what I'm doing here, is that this would be 2 pi over 6. This would be 3 pi over 6, 4 pi over 6. And then here would be 5 pi over 6. So that doesn't reduce down. But these relate in terms of counting of just the reduced form of those fractions. See, 5, 6, 7, 8. I'll just write these out so you can see all of them. 9, 10, 11, and then 12. All right, so there are the measurements in radians. Oh, sorry, 30 degrees, so that's going to relate to pi over 6. So when trying to draw these angles, still thinking a little bit in terms of degrees, but really it's about how we're dividing up the circle. Is it these increments of fourths or thirds or sixths? And then from there, I just count around the circle. There are ways, if you're great at memorizing, then go for it. I'm not so great at memorizing, so I like to go back to the basics. So in these videos, you'll hear me counting around the circle. It's just what I do, but you may have shortcuts and ways to get there, and absolutely use them. But I just like to reinforce these as it just comes down to counting around the circle and just getting the fractions correct. So let's try this out. So let's go through this example with negative pi over 3. So what I'm going to do is recognize that with that denominator of 3, that means we're working with increments of 60 degrees. So just to kind of throw it back to something that we're comfortable with. So what I could do is just kind of look at our system here and just kind of outline that if I have that denominator of 3, I'm going to land at one of those spots. So negative means I'm going to go in the clockwise direction. So here's my initial side right here. I'm going to go counterclockwise, and I just need to go -1 of those wedges. So made this probably more complicated with all these lines here, but really it's just going to come down to going -1 of those 1/3 pieces. So that angle measurement there is -pi/3, and I would just draw my ray there, and that would be it. So going -1 of those wedges would look like that. 17pi/4. So seeing that denominator of 4, I'm going to think of the increments of 45 degrees. Or really, it's like taking our value of pi and cutting it into fourths. Now, there are ways to think about this in terms of 2pi. And oh, sorry, I'll go back to that last one and talk about coterminal angles, but we're just starting this one. So I'll finish this and then go back about coterminal angles. This one is going to go beyond 2pi, because I could imagine like here 0, 2pi, which in terms of fourths would be the same thing as 8pi/4. So I can see I'm going beyond that. You could even think could extend further to 4pi, which would be 16pi/4. So I'll come back to that, but let me go the long way of just counting around the circle. So it's positive, so I know I'm going to be going counterclockwise, and what I'm going to do is just go around and count how many times I pass these lines that I drew. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So what I did is I have those wedges that represent a fourth, and I just counted 17 of them until I ended up right there. That makes sense. I can see that at 4pi, that represents 16pi/4, and to get to 17, we would just need one more beyond that. So my graph right there is going to look like this. So, coterminal angles. So where this is a measurement of 17pi/4, what we can see is we had 2 revolutions in there. So what I could do is imagine, find out what that distance would be of what if I had 17pi/4 but took away one of the revolutions. Now we have to have common denominators here, so what I'm going to do is go ahead and change this to 17pi/4 minus 8pi/4. Now, little fraction review here. So this works because 8 divided by 4 is 2, so that's perfect. Carrying this out, your denominator stays the same. Pi is going to stay up there. So what it really comes down to is just looking at 17 minus 8, which is 9. And that makes sense too, because 8pi/4 would land there, and then we would need one more, which would take us to 9pi/4. And I could do the same thing, so that's a coterminal angle. I could do the same thing again, take 9pi/4 minus 2pi, which is 8pi/4. And again, it comes down to denominator stays at 4, we'll still have pi, 9 minus 8 is 1. And that's how we can see that pi/4 distance right there. So it's just changing to radians instead of thinking in increments of 360 degrees. Now we're thinking in terms of 2pi. It's like taking pi/4 and adding or subtracting increments of 2pi like we did before. So let's go to this one up here and think about the same thing. So in that previous example, I subtracted 2pi. I could have been adding it on. That's completely fine. So with this one, let's go ahead and add 2pi. So -pi/3, and I want to add a full revolution of 2pi. Now those have different denominators, so I need to make sure they both have a denominator of 3. And to get 2 out, I would need a 6 in the numerator. So 6 divided by 3 would give me that 2. So again, the denominator stays the same. Pi keeps hanging out. So what this really comes down to is a -1 plus 6, which is 5. And we could just make sure that makes sense. So 1, 2, 3, 4, 5. Awesome. Finding another one, we could add 2 pi again. So taking that 5 pi over 3 and add on another revolution to that. So denominator stays at 3. We keep pi in the numerator. 5 plus 6 is 11. And that would be another coterminal angle. All right, so graphing them comes down to those increments and just counting around in the correct direction. And the coterminal angles come down to adding or subtracting increments of 2 pi. Let's do 2 more here. So with that 6 in the denominator, I'm going to think in terms of increments of 30 degrees. So I'm just going to visualize 30 degrees is the messy one because there's so many of them. Okay, I'm going to go negative, so that means we're going clockwise, and I want to go a distance of 5. So I'm going to go 1, 2, 3, 4, 5. So that's our 5 pi over 6. And for the ray, it goes right there. So then adding or subtracting increments of 2 pi. So I'm going to have this negative 5 pi over 6, and I'm going to add 2 pi. However, I need that denominator of 6, so to get 2 pi, I would need a numerator of 12. So negative 5 plus 12 is 7 pi. Then to that, we could add another revolution, which would be 19 pi over 6. All right, one more example here. So positive 9 pi over 2. So visualizing halves, it does relate to increments of 4. So it does relate to 45 degrees, but really we could think in terms of increments of 90 degrees. So we could just focus on basically landing on the X and Y axes. So it's positive, so we're going counterclockwise. So I'm going to go 1, 2, 3, 4. 5, 6, 7, 8, 9. So where we're landing is at that 90-degree angle right there. So we have 9 halves there. And then I'm going to go ahead and take away 2 pi from this, just because I like to go towards the smaller numbers if I can. Taking away 2 pi, let's see, denominator of 2. So I'd have 4 pi. So that'd be a 5 pi over 2, and then if I took away 4 pi over 2 again, that would be 1 pi over 2, which makes sense because that is our 1 pi over 2 right there. That's another reason why I like to go towards kind of the smallest numbers, is that then I can usually end up at a number that I could visualize if there were multiple revolutions going around. So those are measurements in radians. Degrees and radians. Oh, sorry, there's a little bit more here. Okay. This video is getting a little bit long, but this will be fast because it'll mostly be with the calculator. This right here, we've actually done already. But just to go through, I'm going to do this fairly quick, of filling this in. So I have my key values of, I know that's 0 radians, pi radians. And then what I would do is start with the 45s. So this is like 1 pi over 4. This is 2 pi over 4, which is pi over 2. 3 pi over 4. 4 pi over 4. 5 pi over 4. So what I'm doing is just counting around the circle. 6 pi over 4. 7 pi over 4. And filling it in just like I did on those separate circles, this would just be all together. And then for our 60 degrees, so that was a third, 2 thirds, pi is 3 thirds, 4 thirds, 5 thirds, and 6 thirds, which is also just 2 pi. And then filling in the 30s. So this is pi over 3, and then we have, 6. 2 pi over 6, 3, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's the spots where they overlap with each other that you just want to be careful of, but it's just a matter of counting around the circle using these different denominators. So that's how I'd fill it in. I highly recommend practicing what I just did there. I know I went through it quickly, but take your time with it and just really visualizing how those angles relate to each other and their values in radians versus degrees. Now, actually converting degrees to radians, we're going to use these two formulas. Degrees to radians, you use a pi over 180 to convert. And how I think of it is you want this cancellation of units. So like here we have something that's in degrees. In order to cancel it out, you want to divide it away. So that'll cause the cancel. So that gives you pi in the numerator and then the 180 degrees in the denominator. But really what we're multiplying by there is just a version of 1, because those two things are equal to each other. Pi radians is the same exact thing as 180 degrees, but it's just a unit conversion so that we get degrees to cancel out, and then we're just left with radians. If we start with something that's in radians, we want to divide out radians so that those units cancel out with each other, and then we're just left with something in degrees. So we're using the same unit fraction, that value of 1, it's just we change numerator into to denominator so that those units cancel out. So let's try this out. I want to convert 200 degrees to radians. So I know I'm going to be using this fraction with pi and 180 degrees. The tricky part is just getting the order right of what goes in the numerator versus denominator. And how I approach it is thinking of dividing away the units that I'm starting with. So I'm starting with degrees. So I want to divide away those same units. And what I want to be left with, which goes in the numerator, are the units I want, which is going to be pi. So with this, we can go to our calculator. So I'm going to use the Desmos calculator. So this is the same thing as 200 times pi over 180. And I'm just going to grab a decimal of 3.49. So 3.49 radians. Now with radians, sometimes we don't write the units, so if it's left blank, assume that it's radians. When you have degrees, you always have the symbol of degrees. So if this just had 200 with nothing and it said 2 degrees, then you would have 200 radians that you're converting to degrees. So degrees always has a symbol. With radians, sometimes the word could disappear, so if there aren't units, assume that it's radians. All right, starting with something that's in radians and going to degrees. So I'm going to use pi and 180. I want to get rid of radians. So I want to divide away that value of pi, and I want degrees, so that's going to go in the numerator. So with our calculator, we'll go 7 pi over 9 times, what was it, 180 over pi. So that's going to be 140. And then we want to make sure our units here are degrees, so we need to include our unit symbol. Our last one here is 5 radians, and we want to change that to degrees. So I want to divide away radians. I want to get rid of radians, and I want degrees, so that's going to go in the numerator. So in our calculator, 5 times 180 divided by pi is 286.48. And then I just need to include my units, which we converted to degrees. I have degrees. So there's our actual conversion to moving between the two measurement systems. Also, we'll have these key ones that we refer to based on how we divide up our circle.